Third class is figuring out the sizes of sets of things. And again, we're going to continue with some sort of standard tricks and rules tricks that we call rules for counting the sizes of things. First one is really easy looking, but actually is often very, very powerful. And it's just called the complement rule. So it says if U is a finite set and A is a subset of U, then one of the ways to figure out the size of A is to say that it's equal to the size of U minus the stuff in U that is not in A. It's a weird looking definition. Here's the picture of it. We use the letter U here to stand for universe. So there's a big universe, that's the set, a big set. And inside of there, we have the set A that we want to know the size of. And it may be that actually there's some way for us to easily know what the size of U is. And there's also an easy way for us to know what the size of U minus A is. That's this thing out here, everything that's not in A. So then to know the size of A, we take the size of U, we subtract everything that's not in A, and what we're left with is the number of things that are in A. And this is kind of interesting because it's really useful for us in what we do, but actually it's sort of a deep principle that's been applied in physics, and there U really is the universe, and the size of U is really the mass of U, which they have sort of good estimates for. And the stuff out here is the stuff that we can observe. So the things we can see through whatever machines we have. And so in physics, what they discovered quite a long time ago is that we have an estimate of the mass of the universe, and there's the observable universe, the stuff we can see, and the stuff we can see doesn't nearly come close to adding up to the mass of the universe. So there's this must be a whole set in there of things we can't see. We can figure out its mass by subtracting this part. And this is you've heard of dark matter. It's this stuff we can't see, but we somehow know it exists. And it's really because of this reason, that the stuff that we can see doesn't add up to enough mass to be the whole universe. So there must be some stuff we can't see. Okay, but that's just philosophizing. Here we're going to use it in a very concrete way. So let's see an example of how we can do this. Let's say U is equal to the set of 8-character strings over lowercase English alphabet and the digits 0 through 9. Okay. So this is a set of size 36, 26 letters, and 10 digits. So that's U. So think of this as just 8-character strings, basically, that only use basic things. And we'll have a set A whose size we want to know, which is set of 8-character strings that contain at least one digit. And digit here is one of these integers, 0 through 9. So have you ever seen kind of requirements like this before? Yep.
Password?
Yeah. Every time you go to sign up for some new site, it asks you for a password. It tells you it must be at least this long, must be at least that long. You try your favorite password, and then it says, no, you have to have at least one digit, or you have to have at least one special character or something. So this is like a sort of a baby model of what might be a password or even a username system. Who knows? All right, so we'd like to know the size of A. And knowing what we know so far, you would be tempted to think, well, let's try and use the product rule to figure out the size of A. So I'll write out the characters one at a time, but what you'll realize if you try to do that is the number of choices that you have at each step depends on what you chose previously. In particular, if I have already chosen a digit among my first I characters, then when I'm choosing the I plus first character, I'm free to choose anything, a letter or a digit. On the other hand, if I get to the last character, the 8th character, and I haven't chosen a digit yet, well, the last one has to be a digit. And so you see that it's going to be hard to think of a procedure where no matter how the procedure executes, you have the same number of choices at each step. So there's ways around that where you could try and say, let's break this up into the strings that contain exactly one digit and the strings that contain exactly 2 digits and the strings that contain exactly 3 digits and 4 digits and so on, all the way up to 8 digits. Count each of those individually and then add them all up, but you see that's going to take some time. The nice thing about this is the complement rule is, yeah, the set A seems to be sort of difficult to figure out the size of, but the set U minus A, what is that? Well, that is 8-character strings that have no digits. But that's just 8-character strings over the alphabet A, B, C, up to Z. That's kind of a simple thing to count, right? So let's figure all these things out. What's the size of U? 8-character strings over a 36-letter alphabet. How many choices for the first letter? First character? 36. How many choices for the second? 36, 36, 36, 36. So applying the product rule with the procedure being we write down the characters one at a time, one after the other, we quickly get the answer that the size of U is 36 to the power 8. What about the size of U minus A? Well, that's 8-character strings over a 26-letter alphabet. So how big is that? Yep. It's 26 to the 8. It's the same thing. We just pick the first character. We have 26 choices. Pick the second character. We have 26 choices. Pick the third character. We have 26 choices. Nothing depends on what we picked before. We always have all 26 choices. So that's going to be 26 to the 8. And now we know the answer. The size of A is, where are we here? Size of A is equal to the size of U minus the size of U minus A. So you take all the possible strings and take away the ones that are not valid passwords, and what you're left with are all the valid passwords. Easy. Okay. All right. So that's the complement rule. The next one is called the sum rule. And it says if A1, A2, and all the way up to AM are pairwise disjoint sets, then the size of A1 union A2 union A3 union all the way up to AM is just equal to the size of A1 plus the size of A2 plus the size of A3 all the way up to the size of AM. So there's a very important condition here, and that requires that these things be pairwise disjoint. Pairwise disjoint means if I take any two of them, let's say AI and AJ, where I is not equal to J, then their intersection is empty. So if we draw that in terms of a Venn diagram, we have the set A1, completely disjoint from it, we have the set A2, completely disjoint from those two, we have the set A3, and so on, all the way up to the set AM. And so if I want to know the size of the union of those things, I just count all the things in A1, I count all the things in A2, all the things in A3, and so on up to AM. And I didn't count anything twice, so that's exactly the size of the union. Is that clear? Okay. All right. So that's an easy one. And we'll use an easy example. So back with the same sort of setup here, let's say I want, so these things here, these 8-character strings that contain at least one digit, let's call them valid passwords. And now let's say how many valid passwords are there whose length is at least 6 and at most 8. Okay. So this is the set of things that I want to count. This is my set A. It's the valid passwords whose length is at least 6 and at most 8. And a valid password is a string that contains at least one digit. Okay. So this is my set. We'll call that thing A. And we'll say we can write A is equal to A6 plus A7 plus A8, where, you know, A6 is the set of valid passwords. I should be careful. Union. This is a 7 valid passwords of length 6, and A7 is the set of valid passwords of length 7, and A8 is the set of valid passwords of length 8. Okay. So the set A that I'm interested in are the passwords whose length is of length 6, of length 7, or of length 8. So we use the sum rule. We need to check, make sure that these things are pairwise disjoint. Are there any passwords of length 6 that are also passwords of length 7? No, right? The password has a certain length, and it's in one of these sets depending on its length. It's never in 2 of these sets. So these things are indeed pairwise disjoint. So that means that we can apply this rule to get that the size of A is the size of A6 plus the size of A7 plus the size of A8. We've already seen how to compute the size of A8. That's this calculation here. Size of A8 is equal to 36 to the 8 minus 26 to the 8. I don't think it's a big stretch then to compute the size of A7 to be 36 to the 7 minus 26 to the 7. And nor is it a stretch to compute the size of A6, the number of passwords of length 6, to be 36 to the 6 minus 26 to the 6. And now we add all of this together. Okay? So the size of A, the number of these passwords is 36 to the 8 plus 36 to the 7 plus 36 to the 6 minus 26 to the 8 minus 26 to the 7 minus 26 to the 6. And if you have a calculator, you can write down that number. It's not that big, actually. I've got them both here just to So that's the number of valid passwords of length 8. And what if I count all the passwords of length 6 and all the passwords of length 7 and all the passwords of length 8? Do you think that's much, much bigger? I think it's like 3 times bigger. Not even close. It's actually So if you compare those two numbers, you see that even the first 2 digits are the same. They only start to differ in the 3rd digit. So it's only there's only a as a percentage, it's only a few percent more passwords that you actually get when you allow passwords of length 7 and passwords of length 6. Okay. So, questions? All easy? So when you see a statement like this, like the sum rule, it says how to compute the size of the union like this, but it has this condition, you should immediately ask, well, what if my sets aren't disjoint? What's the rule then? And for that, it is something with a fancy name. The principle of inclusion-exclusion. And so the basic version of it is if I have 2 sets A and B and I take their union, then the size of that thing starts out the way you would expect. There's the size of A and there's the size of B, but then you subtract the size of A intersected with B. So why is that? So here's the set A. No, I don't need color for this. Here's the set B. We can even draw some elements in here to see what's happening. So, and these are the elements in A union B. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. And these we can just count. We can see them. Okay? So if we take the size of A plus the size of B, so size of A is 6. Size of B is 1, 2, 3, 4, 5, 6. Then we get 12. And why is it 12? Well, it's 12 because when we counted A, we counted these 2 points. And when we counted the size of B, we counted these 2 points. So these 2 points, they got counted twice. That's why we get an answer that's 2 more than the truth. Okay? So this thing here, these things that we count twice, this is the A intersect B. We've counted the points in here twice, so we should subtract that. And now indeed, if we apply this formula, 6 plus 6 minus 2 is indeed equal to 10. Okay. So that's the basic principle of inclusion-exclusion. And let's do an example. Not passwords anymore. So count this. The 17-bit binary strings that start with 0, 1, 0 or end with 1, 1. Okay? So I want to count all of the 17, the length 17 binary strings. So these are strings over 0 and 1. And I only want to count the ones that start with 0, 1, 0 or the ones that end with 1, 1. Okay? And, well, the first thing we could ask is, all right, maybe we can apply the sum rule. But it's not hard to see that actually these 2 sets aren't disjoint because let's put in some 12 bits here and then finish with 1, 1. This is in the set A because it starts with 0, 1, 0, but it's also in the set B because it ends with 1, 1. So it's something that we should count, but we only want to count it once. Okay? So we don't get away just using the sum rule. Instead, we have to use the principle of inclusion-exclusion. And now we need to figure out the sizes of these sets A, B, and A intersect B. So the strings in A, what do they look like? Well, they start with 0, 1, 0. And what comes next? Yep. 1 or a 0. and then after that, a 1 or a 0, and then after that, a 1 or a 0, and then after that, a 1 or a 0, and so on. So they start with 3 fixed characters, and then they have 14 characters, each of which I have 2 choices for, 0 or 1, 0 or 1, 0, 1, and so on. Okay. So a way to generate these things is you first write down, or a procedure to generate one of these things is you write down 0, 1, 0, and then you make a choice whether you write 0 or 1. Then you make a choice whether you write 0 or 1. Then you make a choice whether you write 0 or 1, and so on. At each of these 14 steps in this procedure, you have 2 choices. So the size of A is 2 to the 14. All right, so this is what the sort of prototypical thing in A looks like. What about if you want to write down a string in B? What do you do? Yep. Yep, so you finish off with 2 1s, and then, I don't know, come back to the beginning, and then you put a 0 or a 1 here, a 0 or a 1 here, a 0 or a 1 here, and so on. So those guys look like this, where you have a choice of 0 or 1 at each of these positions. How many positions are there? There's 15 positions, 17 minus the 2 that are fixed at the end. So that means the size of B is 2 to the 15. And now we want to know the size of A intersect B. So these are the strings that start with 0, 1, 0, and they end with 1, 1. So those A intersect B strings, they look like this. 0, 1, 0. There's something in between. There's 17 minus 5, 12 characters in between. And so if we want to write one of these, we write 0, 1, 0. We choose whether we write 0 or 1. We choose whether we write 0 or 1. We choose whether we write 0 or 1. Each time we have 2 choices. We do that for 12 steps. And then we write 1, 1. There's no choices there. Okay? So 12 characters here that I get choices for. So that's 2 to the 12. Okay? So then the answer is the number of strings that 17-bit binary strings that start with 0, 1, 0 or end with 1, 1 is 2 to the 14 plus 2 to the 15 minus 2 to the 12, which is 45,056. Yep.
Just go over how you got A intersect B equals 2 over 12.
2 to the 12. So the strings in A so all of these strings that are in A intersect B, that means they're both in A and they're in B, which means they start with 0, 1, 0, and they finish with 1, 1. So that's, of the 17 characters in that string, 5 of them are fixed, and that means that there's 12 that we still get to choose. And now you apply the product rule to those choices, and you get 2 to the 12. Okay? All right. But now if you're a sort of nervous person, you say, hey, wait a minute. You showed me the sum rule, which let me figure out the size of the union of M sets, any number of sets here. I could figure out the size of their union. And then you showed me the principle of inclusion-exclusion, which let me figure out the size of the union of 2 sets. But what about more than 2 sets? So the answer is it gets messier. And I think for now we will only see the 2 and 3 set version of this thing. The multi-set version is not significantly more complicated. It's just you hardly ever use it fully. So let's do the 3 set version, which is I have 3 sets, A, B, and C, and I want to know their size. I start out the way you would expect. And let's do this with a picture. I have A, I have B, and I have C. Those are my 3 sets. Here's an example of some stuff. And in this example, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. And if I look at the formula that I'm developing here, let's see what's happened so far. So I added A plus B plus C. So the points over here that are only in A, they're counted there. The points that are only in B, they're counted there. And the point that is only in C, it's also counted there. But what about this point? How many times was it counted? Twice. I counted it once when I was adding up the size of A, and once again when I was adding up the size of C. And what about this point? It was counted twice. And what about this point? It was counted twice. What about this one? It was counted 3 times. All right, so let's add our correction term. So we have points that are in A and C. We better subtract those. And we have points that are in A and B. We better subtract those. And we have points that are in B and C. We better subtract those. Let's check if our formula is right now. Okay, so this point here that's in A and B, how many times has it been counted now? So I counted it once in A, once in B, but then I subtracted it once because it's once in A, once in C, and then I subtracted it once because it's in A and C. So this has only been counted once now. This one here was counted once when I was counting up B, once when I was counting up C, but then I subtracted it once because I took away B intersect C. And the same thing with this point. Counted once for A, counted once for B, but then removed because one of those was taken away because I removed size of A intersect B. What about this point? Yeah.
Would it be counted 0 then?
Yeah. So it was counted 3 times because I counted it in A, I counted it in B, and I counted it in C. But then I looked at the intersection of A and B and I subtracted 1 from this point. And I looked at the intersection of B and C and I subtracted 1. And I looked at the intersection of A and C and I subtracted 1. That means it's been counted 0 times. So this formula is not correct yet. It needs one more corrective term. Which is, I need to add back in all of the points which appear in all 3 sets. Because right now they're not counted at all. So first time I triple counted them, and then I made up for that 3 times, which left me with no counting, so I need to fix them all up. questions? You believe that? And you'll see if we do that here, we'll get the answer 10. So that last term that we just added puts this thing back to a 1, and we get exactly this 10 points here. Is that clear? All right. So we're done with the sum rule for now. Let's try this principle of inclusion-exclusion for 3 sets. And since we've already done some of the work, we can just make this question a little bit harder. We'll say, count the 17-bit binary strings that A is begin with 0, 1, 0. B is end with 1, 1. Or C is have 0, 1 at positions 6 and 7, respectively. Okay, so the A strings, you know what they look like, 0, 1, 0, followed by 15 of whatever you want. The B strings, not by 15, by 14 of whatever you want. The B strings, so this is 14. The B strings start with 15 of whatever you want, and they finish with 1, 1. It's 15 of those. And the C strings, they start with 1, 2, 3, 4, 5 things. And then I see 0, 1. So now I've seen 7 things. And then I see 10 more of whatever I want. 10 of these, 5 of these, and these 2 in the middle are fixed. Okay? Yep.
Could you go over again why you added back the intersection of A, B, and C?
Yep. That's because if I cut the formula off here, then the stuff that is in the intersection of A, B, and C, that means it's in A, it's in B, and it's in C. So that means I counted it when I counted A, I counted it when I counted B, and I counted it when I counted C. That means that stuff's been counted 3 times. Now, I've subtracted it when I subtracted A intersect C, because that stuff is also in, it's in A and C. And I've subtracted it again, and I've subtracted it again. Now it's been counted 0 times. So that's the only stuff that's not correctly counted at this point. So we need to add that back in and make sure we count it once. Yep.
Is there a formula that will work for any amount of sets, or did you just have to expand?
There is a formula, but it's basically a sum, an alternating sum where there's a bunch of things with pluses in front of them and a bunch of things with minuses in front of them. And so what you do is you add up all the sizes of the sets individually. That's what we've seen here, A plus B plus C. Then you look at all the pairs of sets, and you subtract all of those, the intersections of those pairs. Then you look at all the triples of sets, add those back in. Then you look at all the 4 tuples of sets, subtract all those. Then all the 5 tuples of sets. And with 3, it doesn't get overwhelming. You only get a few terms in this thing. But if I have like 10 sets, then already the number of pairs is 10 times 90 is 45. And the number of triples is something like Yeah, 10 choose 3, which we'll learn in a second. But these numbers, I mean, you just get a lot of terms that you have to calculate. So it gets sort of tiring after a while. Yeah?
Theoretically, could you have like an infinite amount of sets that intersect?
Well, if you have an infinite number of sets, then you have to be careful that you are, if the sets themselves are finite, right? So we're talking about counting the size of things, so we seem to suggest that they're finite, right? So if you have finite sets, so there's each of some size, then, well, the number of subsets of a finite set is also a finite set. And so that means that you can't really have an infinite number of sets for these questions to make sense. It means, so if you have an infinite number of sets, that means in there you have two sets that are the same because there's only actually a finite number of these things. So you could reduce the infinite case to a finite case. Or the problem doesn't make sense because you're talking about sets of infinite size, in which case, I mean, how big is the set of integers? How big is the set of real numbers? They're all of infinite size, sort of. So. Okay. So let's do this thing. So we need to apply that formula. So we need to know the size of A, which luckily we have already done. That was 2 to the 14. The size of B is 2 to the 15. What about the size of C? That's these strings here. Yeah.
Is it also 2 to the 15?
2 to the 15, because I get to 5 times I get to make a choice here. Each one has 2 options, and 10 times I get to make a choice here. That's 15 choices. So that's also 2 to the 15. Now I need A intersect B, which I already have. That was 2 to the 12, if I'm not mistaken. Yep. Now I need A intersect C. So those are the strings that start with 0, 1, 0. And then I see, so 0, 1, 0, and then I see 2 of whatever I want. Then I see a 0, 1, and then I see 10. Yep. 2 to the 12, right? 2 choices for this, 2 choices for this, 2 choices for this, 2 choices for this, and so on. The other 5 positions we don't have a choice. Okay? So that's 2 to the 12. And I also need to know the size of B intersect C. What does B intersect C look like? Well, B intersect C looks like this. Five free choices. Then, because they're in C, it's a 0 and a 1. And so then I have 8 free choices. And then no more choices anymore because they have to finish with 1, 1 because they're supposed to be in B. So how many of those? 2 to the 13. 5 plus 8 is 13. So that's 2 to the 13. And now I have almost everything that I need. Just that last term, I need to add back in all the strings that start with 0, 1, 0 and have 0, 1 at position 6 and 7 and finish with 1, 1. So those look like 0, 1, 0, 2 choices, 0, 1, 8 choices, and then 1, 1. How many of those are there? That is is 2. So 2 choices here, 2 choices here, 2 choices here, each of these things. That's 10 steps in my procedure. Each one has 2 choices, so it's 2 to the 10. So that's the size of A intersect B intersect C is 2 to the 10. And now I have my answer, which is the size of A union B union C is equal to 2 to the 14 plus 2 to the 15 plus 2 to the 15 minus 2 to the 12 minus 2 to the 12 minus 2 to the 13 plus 2 to the 10. So, and I have that number written down. Before I write it for you, guess for me, oh, maybe I don't have it written down. No, I didn't bring it with me. Make a guess about whether, so the number of 17-bit binary strings, there's 2 to the 17 of them. Do you think that this is more or less than half of them? So the answer is it's slightly more, but it comes close. There's about 66,000 of them, of these guys, and the half of 2 to the 17 is 65536, so 65,536. So a little bit more than half of the strings satisfy this condition. Okay? Good. So, questions about that? So, no questions means either everyone understands or no one understands. Which is it in this case? Okay. All right, so if you do understand, if you're one of the ones who does understand or feels like you understand, be careful. This material is presented in a way to make it look deceptively simple and straightforward, and you just do the obvious thing and it works. If you're feeling that way and you haven't started on the assignment yet, then I suggest you start working on the assignment. So that may give you a sort of reality check about how difficult these things are. Yes? Why is what? There's no good reason other than it adds up to a number that's more than half. But you can kind of guess here, you have 2 to the 15 plus 2 to the 15 inside of here. That's 2 to the 16. So that's half of 2 to the 17 already. And now you just got to make sure that, you've also got a 2 to the 14 and subtracting some 2 to the 12s, but you stay above half. Yeah. But there's the key right there is these two things. So I'll just make a note. So I said that this thing extends to many sets, but the formula gets very complicated. And because of that, it's hardly ever used. Instead, what frequently happens is you use simpler versions of this thing. And one of my favorite ones, one of the ones I use all the time in my research, is like the easiest version imaginable. The size of A union B is less than or equal to the size of A plus the size of B. Because, certainly, certainly size of A plus the size of B is bigger than this thing because this thing subtracts stuff. So very often, if you don't want to know the exact size, but you just want some loose bound, you can use something like this. And more generally, when you have one of these things that's getting out of control like this, you can often get upper and lower bounds by stopping after some number of things. Like the one I just showed you is, if you stop after just adding up the sizes of the sets, you get something that's bigger than what you're trying to count. But at least if you know that answer, you know it's not worse than that. If you then subtract off all the double counting here, you get something that's smaller. And often when you do that, you realize the difference between the thing that's bigger and the thing that's smaller is not so great. I don't care about the fine details of it. And you see that is kind of happening here. The big stuff is already captured here. 2 to the 15 and 2 to the 15. These are bigger than any of, they're both, each of them is twice as big as any of the numbers on the board here. And in fact, they're, like 2 to the 15 is 8 times bigger than either of any of these other numbers. So somehow often the real essence of the problem comes in just when you add up the sizes of the sets. Okay, but we won't do that so much in this course. All right. Next up is permutations. What are permutations? Give you an example. Take a set S with elements A, B, C, D. No, let's not go that big. Let's just say A, B, and C. So basically, the permutation is just me writing out the set S in some order. So for example, the permutations of S are the sequences that I can make by writing each element of S exactly once. So I get ABC, I can get ACB, I can get BAC, I can get BCA, I can get CAB, and I can get CBA. And that's all I can do with a 3-element set like this. So this thing here is the permutations of the set S is A, B, C. So each permutation is a sequence in which each element of S appears exactly once. Okay. So here's a theorem. The number of permutations of an n-element set is n factorial. And in case you forgot, since last class, n factorial is defined as n times n minus 1 times n minus 2 times n minus 3, and so on, all the way down to 1. So how would you prove that? Yeah.
So because order matters, you first pick a character for the first one, so you have in this case 3 options. And for the next character, you've already picked 1, so you have like 3 minus 1 options, 3 minus 2.
Yeah. Yeah. So in fact, we already proved something stronger than this last class, because last class we looked at these functions from a set A, these one-to-one functions from a set A onto a set B, up to n. And then you have the elements of S. Well, let's just think of it this way. 1, 2, and 3, A, B, C. So when I write down a permutation, something goes at position 1, right? It's either A, B, or C. So there's 3 choices for position 1. Or you can think of it as there's a function that takes the argument 1, 2, or 3 and gives me one of A, B, or C. And it's an onto, it's a one-to-one function. That's because each element here appears only once. So really, these things are, permutations are the same as one-to-one functions from the integers 1 through n onto the set S of size n. And we counted the number of one-to-one functions from one set onto another, and it was, if this thing had size m and this thing had size n, that was, what did we say? N factorial divided by n minus m. N minus m factorial. But in this case, we have n and n on each side. So this is n factorial divided by 0 factorial, which is n factorial. Or if you don't like to use an old theorem, just use the product rule and say the way I write down one of these permutations is I pick an arbitrary element from S and make it the first one. Then I pick an arbitrary element that I haven't picked yet and make it the first one, the second one. So that's n choices for the first one, n minus 2 for the second one, n minus 1 for the second one, n minus 2, n minus 3. And then when I get to the end, there's only one element left, so there's only one choice. So that's clear, easy. Let's check here. 3 factorial is 3 times 2 times 1, 6. And 1, 2, 3, 4, 5, 6 permutations. Good. It's always good to check on an example. If I want to take a set and impose an order on it, then how many ways are there to do that? It's the size of the set factorial. Let's start with a definition. I'll say n choose k is equal to the number of k element subsets of an n element set. So let's do an example and say, take a set S, which has A, B, C, D, E in it. So this is n equals 5, and we'll take k equals 3. And how many subsets of S of size 3 are there? Well, we can start writing them down. So A, B, and C is one of them. A, B, D, A, B, E, A, B, C, A, B, D, A, B, E, A, C, D, A, C, E, and A, D, E, B, C, D, B, D, E, B, C, E, and finally C, D, E. Okay? So these are all the subsets of S of size 3. And the number of them, by definition, is 5 choose 3. So that's just the definition of this, what this thing means here. And in this particular example, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. So by doing this and making sure that I didn't miss any subsets, you would arrive at the conclusion that 5 choose 3 is equal to 10. Of course, this is error prone, and we don't want to have to do this for every sort of pair of integers here. So we'd like a general formula. So let's think about how we would come up with that, or some easy cases. So what about n choose 0? So I have a set S of size n. How many subsets of size 0 does it have? Yeah, there's exactly one. It's the empty set. So n choose 0, that's 1. What about n choose n? How many subsets of size n does it have? Just one. It's the whole thing. What about n choose k, where k is bigger than n? So I have a set of 10 things. How many subsets of size 11 does it have? None, right? It has no subsets larger than 10. So for k bigger than n. And we won't worry about k less than 0. So we won't ask for subsets of negative size. There are maybe reasonable interpretations of what that means, but not for what we're doing in this course. All right, so we know a few values of this thing. But I'd like to know the general thing, and what I'm really interested in is when k is between 1 and n minus 1. Okay, so let's work in that range. And here's the theorem for k in 1 up to n minus 1. N choose k is equal to n factorial over n minus k factorial times k factorial. Okay. So let's think about how we could prove that. And I'll show you a proof of this today. It's not very hard, but it uses something that turns out to be a non-intuitive but really useful technique. So once you start working in combinatorics, you'll realize there's this really sort of neat trick that's called double counting. And it doesn't mean the mistake we were making when we were trying to add up the sizes of sets. It just means counting the same thing in two different ways. So this sort of usual thing with the trick is you pick some set A that's helpful for you to work with, that you can figure out the size of A in two different ways. And you count one way, and you get some formula F for the size of A. And you count another way, and you get a different looking formula, G, for the size of A. Both of those things are correct, because you were careful and you did all your work correctly. And what you then learn is that G is actually equal to F, even though those two formulas maybe don't look alike at all. It's a really useful trick in combinatorics, and we'll use it now. So we'll say, let's take A to be the K element ordered subsets of S, of an n-element set. Okay, so what does the ordered mean? Well, that means that, if my set S is this, A, B, C, D, E, then I count A, B, C, but I also count A, C, B, and I also count B, C, A, and I also count B, A, C, and I also count C, B, A, and I also count C, A, B. So these things are all ordered three-element subsets of S. So you can think of them as, you call them ordered subsets because you want to say that set, meaning that each element of S appears only once, so each element is unique, and ordered really because you mean they're actually sequences. Okay. So that's the set A, this thing that's going to be sandwiched in the middle of this double counting that we're going to compute the size of two different ways. Okay. So if I want an ordered, let's say, for concreteness, three-element set of S. So that means I want three things from S, three different things from S, taken in order. How many choices do I have for the first thing? What's that? 5? Yeah. So 5 in this case, and in general you have n choices. You can take anything as the first thing in your ordered sequence. How many choices do I have for the second thing? The same? No, this ordered subset means that the same element doesn't appear more than once. Okay. So then I have 4 for the second one, or n minus 1, and then I'll have 3 for the third one. Okay. So that means, so by the product rule, here's a way to make these ordered subsets of size k is first I pick the first element and I have n ways to choose that element. Next I pick the second element, but I can't choose the first one again. Yep. No, as the first one I pick whatever, something like, A. Then after that I can pick any of these things. So don't confuse ordered and sorted. I think that's maybe what's happening. So if I pick as my first element C, then I'm allowed to take A as my second element. There's nothing wrong with that. So it's not, ordered just means there is a specific order. I list them in a specific order, not that they're in sorted order or anything. Okay, so I can take any of these 5 elements, and then any of these 4 elements, and then any of these the remaining 3 elements, and that's the way I get this thing. Okay, so n minus 1. For the third one, I have n minus 2, and that goes all the way down to, for the kth one, I have number of options is n minus k plus 1. Okay. So that's it. I'm done counting the size of A here. That's the way it works. So a little bit handy if we write this in this factorial notation. So this is n factorial divided by n minus k factorial, right? N factorial would have us counting all the way down to 1 here, which we're not doing. But so if we write n factorial, we'd better divide by all the stuff we're not doing, which is n minus k factorial. All right. Let's count the size of A a different way. Here's how we'll list all of the elements in A. First thing I'll do is I will pick from S a subset of size k. So for example, here I take one of these things, ACE. So that's a subset of it. And now, this thing, I write down all the permutations of it. ACE, AEC, CAE, whatever, the 6 permutations of that thing. Okay? And so first thing I do is I pick a subset of size k, and then I write down all the permutations of that subset. There's k factorial of them. And if I do that, then I will also see every single ordered subset of S of size k, right? I'm still good. It does the same thing. So whether I pick the subset first and then decide on the order of that subset, or whether I just pick them out in order, I'm going to get every single possible order of size k. How many ways are there to pick a subset of size k out of a set of size n? Well, that's the thing that we're discussing. By definition, that's n choose k. Now, each of those things that I pick creates a big list of actual ordered sequences. The number that it creates is the size of that thing, which is k factorial. Okay. So that's another way to count the size of A, is to say that it's n choose k times k factorial. All right, so here's the punchline. N choose k times k factorial is equal to n factorial over n minus k factorial. So let's divide both sides by k factorial. This goes away, and the k factorial ends up down here. And that's the theorem, right? N choose k is equal to n factorial over n minus k factorial, k factorial. So it's a really powerful trick sometimes to introduce an intermediate set to show that two odd-looking formulas happen to be equal, or to get some quantity to determine the value of some quantity. And in this case, yeah, this is the thing we wanted to learn, n choose k, and now we know what it is. And the way we got there is by counting the size of this set A. Now, if you're unhappy with that, if that bothers you, this sort of proof, or you have trouble getting your head around it, here's another way to think about it. Suppose that I just wrote, I did this thing on this side where I wrote down every possible, in this case, size 3 sequence I could make that has distinct characters from this set of size 5. I get this long thing, really long thing, and this is the size of it here, okay? Which is equal to this thing. That's just normal stuff. Now, I say, well, I don't actually care about the sequences. What I care about are the subsets. And if I forget about the order within the sequences, I'll see the same subset many times, right? I'll see ACE, and I'll see AEC, and I'll see EAC, and ECA, and so on. How many times will I see it? Well, I'll see it exactly the number of ways that there is of arranging permutations of a k-element subset, which is k factorial. So you can also get to this by saying, let's just count the size of A here the way that we sort of naturally would just by picking elements. And then say, but look, for every subset there that I'm interested in counting, it shows up k factorial times in this list of, in this A thing. So the number of things that I'm really counting is this number divided by k factorial. I mean, both of those are basically the same argument. Okay, so that's a good place to leave it for today.